I'm Matt Papanikolaos. I'm one of the organizers here at the Lunar School. Just wanted to say welcome to Tucson, and we have a really enjoyable conference. Just a couple things. We have a few announcements to make, sort of logistic announcements, and then first I'd just like to introduce the organizing committee. So if you have any questions, feel free to contact any of us. And so without you, David Satt from the University of Arizona, Dinesh Thacker, also from the University of Arizona, Rachel Freeze, and myself. So if you have any questions, feel free to let us know. And then we also have other announcements regarding the table.
So on behalf of the math department, I want to welcome all of you. My name is David Gonzalez, and I'm a business manager for the department. I just want to make a couple of announcements. One is, each of you in the folder should have a yellow form such as this. This form, you need to fill it out, and you can do two things. One is mail it to us with all your receipts. We have also given you an envelope with our address, so you can mail it once you get home. Or if you can put your receipts together and fill out the form, we can take it throughout the week. We will be here usually a couple of hours in the morning, and we'll be just outside just in case you have any questions about your reimbursements. We will have on Monday a trip to the Desert Museum. It's a $5 fee that will be collected at when you guys board the bus. Basically, the bus will be straight behind this building, so Helen and Mount. We'll be there at 1 o'clock, and there's a capacity only for 70 participants. So I'm going to keep the form, the signing sheet in front of the building. If you have any questions or if you want to sign up, put your name on it, and then we'll be collecting the fee later on Monday. Then there's a dinner. If you have registered, we'll be at the hotel, at the Marriott Hotel, couple minutes before the dinner, and we'll give you a ticket that will have the choice that you selected, your dinner choice. So we'll give you that when you get to the Marriott Hotel. So I think that's it. If you have any questions, like I said, I'll be in the foyer area, or just ask David or one of the PIs. Thank you very much.
Okay, so who's our first speaker? It's Joe Silverman from the University of Arithmetic.
Thank you. I want to thank the organizers for inviting me to do this. This is actually my first time at Arizona Winter School. So looking forward to it. The 4 topics up there are not today's topics. Those are the 4 talks. So today's background talk. And since there's a significant amount to cover, let me just jump right in and start covering it. So what I'm going to do today is background on both some geometry, some dynamics, and some number theory, which is going to get used in my other 3 lectures, and also Rob Benedetto is going to use some of it, and possibly the other 2 speakers, I'm not sure. So there's not really going to be much in the way of proofs today. It's mostly going to be definitions and setting things up, and statements of theorems, but not so much proofs. Okay, so to start with, what is a dynamical system? Well, basically, you simply have a set and a map from the set to itself. And what we're interested in is iterating the map. So we'll have phi to the n denote just iterating phi n times and applying it to a point x. And what we're interested in knowing is how the iterates affect the points in S. So we define the orbit of a point, so O sub phi of alpha, just to be what happens to the point alpha. The set of points you get is you just repeatedly apply the map phi, and the map alpha moves around the set S. And in some sense, dynamics is the study of orbits, or one might say classifying the points of S according to what their orbits look like. A first very basic dichotomy in orbits is some orbits are finite. So, and in that case, we say that alpha is pre-periodic. For the map phi. And if the number of points is infinite, then we'll say alpha is a wandering point. So a pre-periodic point, right, you start with alpha and you apply phi, and you apply phi, and so on. And eventually you come back and just start looping. Of particular interest, frequently, are the points which actually loop backwards themselves. And those points would be called periodic. And in many situations, the behavior of the periodic and pre-periodic points, well, the distribution of them among the set S is very important in analyzing the dynamics. So just to set some notation, I'll let pre-periodic of phi S. That'll just denote the set of points that are pre-periodic that have finite orbit, and p periodic of phi S would just be the set of points that actually loop backwards themselves, so they're strictly periodic. Okay. So the title of my talk is Arithmetic Dynamics. So the dynamics part I was just explaining is you take a set and a self-map and you iterate and you see what happens to the points. The arithmetic, of course, refers to the questions I'm interested in studying are number theoretic. And there are a lot of different aspects to arithmetic dynamics. I thought I'd just mention two sort of typical problems which will be discussed during my talks, although there are lots of other problems that are studied. So the first problem would be, well, for example, suppose you just take a polynomial map from C to C or something, where phi is a polynomial, say, with rational coefficients. There are lots of periodic points and lots of pre-periodic points in complex numbers. So one might ask, how big is, say, the set of pre-periodic points that are actually rational numbers? Is that set finite or infinite? If it's finite, how large can it be? Can we bound it in terms of phi? Can we bound it even independently of phi, or mostly independently of phi? So that would be a typical number theoretic question, because we're talking about rational points that are periodic or pre-periodic. Another typical question might be if you take a rational function and look at, at a point, and you look at the orbit of that point, so all the iterates of phi applied to alpha, obviously all those numbers in the orbit will be rational numbers, because you're plugging a rational number into a rational function. But one might ask, are there infinitely many integers in that orbit? When can there be infinitely many integers? Can one classify them? And if there are infinitely many, can you bound how many there are? So these are actually analogs of very classical and important questions in Diophantine equations. The first one is the analog of how many rational torsion points can you have on an abelian variety or an elliptic curve. And the second one is an analog of Ziegel's theorem about which curves have finitely many integer points. Let me put this on top. Okay. So those are some typical questions. So just as with studying Diophantine equations, you really need to use at least a little bit of algebraic geometry. because the geometry, to some extent, determines the arithmetic. So a rational function, maybe I'll just start over the complex numbers, gives a map. Well, it more or less gives a map from the complexes to the complexes, except a rational function like this, so it's a ratio of polynomials, the denominator there will have some poles. Okay? So what phi really gives is a map from the projective line to itself, where, if you want, you can even just think of the projective line as being the complex numbers together with one extra point to infinity to compactify. When you write a rational function like this as a ratio of polynomials, you then define the degree of the map phi to be the larger of the degree of the numerator and the degree of the denominator. I should also mention that when I write it like this, I mean, I'm assuming that f and g have no common factors, because if they do have a common factor, you might as well cancel it out. Okay. All right. So, phi is a map from the compactified complex plane, or from P1. There's, of course, a lot more structure there. And one of the things dynamics does, I mean, when I said that you try to classify the points in S according to what their orbits look like, usually the set S that you're working with has some additional structure. In this case, P1 of C has a topology and even metric on it. So let me just quickly explain one of the ways to put a metric on P1 of C, which is convenient. So what one does is one identifies P1 of C with the two-sphere. Let's see if I can draw a reasonable picture here. Okay. What you do is take the two-sphere and kind of unit sphere and put it sitting in three space with the complex plane being the xy plane. All right? And then what I want to do is I want to identify every point in the complex plane with a point on the sphere. And the way I do that is I take the north pole point on the sphere and take the point in the complex plane, just draw the line connecting them. And that will intersect the sphere at a unique point, maybe I'll call it Z star. So we've identified each complex number with a point on the unit sphere, and the point at infinity, the extra point I've thrown in becomes the north pole in the sphere. And then we can define a metric on P1 by just taking the points Z1 and Z2 in the complex plane, identifying them with 2 points on the sphere, and just taking the distance between those 2 points on the sphere, and for, I'm not quite sure what reasons, historically, people take 1/2 of that. And this is called the coordinal metric on P1 of C. And there's a formula for it that's in the notes that you can download. Oh, by the way, I should mention, I assume everyone knows, that there are sort of expanded versions of all these lectures on the web, and you can download them. So, like, if you'd like to see this messy formula, it's there. So this gives a reasonable way of measuring distances on the sphere. When working with functions in some sort of geometric setting, it's often true that you can change variables and not really change the underlying problem very much. Okay, so in our case, the change of variables will be with automorphisms of the projective line, and those are given by linear fractional transformations. So just AZ plus B over CZ plus D, where the determinant AD minus BC isn't 0, so it's an actual non-constant function. And these, in fact, give all automorphisms of the projective line, at least in the sense of algebraic geometry. However, well, so if you like, I mean, it's almost as GL2, right? Identifying ABCD with the matrix ABCD, except that well, actually, any diagonal matrix acts trivially, because that would just be, F of z equals z. So you really want to mod out by the constants. So this automorphism group of P1 of C is actually the projective linear group. It's just the 2 by 2 invertible matrices modulo the diagonal, diagonals with the same entry matrices act trivially. By the way, if there are questions or anything, feel free to jump in and stop me. I mean, people probably already know most of this stuff anyway, but never hurts. Okay, so linear fractional transformations are a change of variables on P1 because they have inverses, right? You just take the inverse matrix. And there are various ways in which one can use them to change variables on a function. So for example, if I had a rational function, well, I could just compose with f, and that's kind of an invertible thing because I could compose with f inverse. Or I could compose on the other side. Neither of those is good for dynamics. Because if you think about it, if you do that, if you do phi composed with f, and then you start iterating that, the f's kind of appear interspersed with the phis, and the behavior is going to be rather different. So the right way to change variables for dynamics is by conjugation, which I'm going to denote phi super f. So this is a definition. It's just f inverse composed with phi composed with f. And one way to see that that's a good way of changing variables is that if you conjugate and then iterate n times, and it's easy enough to see because of the cancellation of the f's and the f inverses, that's just the nth iterative phi conjugated by f. So it really just comes down to changing variables. So this is the way you should visualize. Unless I got it backwards there. I didn't do it. Yeah, the CF's up here. Okay, so you just get a commutative square. So for example, if you're interested in studying what happens to a particular point, you're just interested in that one point, you could conjugate, for example, to move it to the point 0, which also makes formulas easier. Okay, so if we have a rational function, so P1 to P1, generally, let's let D be the degree of phi. So generally, D will be a D to 1 map. So you take sort of a random point here and take its inverse image, you'll usually get D points in the inverse image. If you're working over an algebraically closed field. Well, over C, say. But sometimes that doesn't happen. Sometimes points come together and you get ramification. And the behavior of ramification as it relates to iterates of phi, to some extent determines a lot of the dynamics of phi on the entire space. Okay? So here's how I want to set things up. Let's take some alpha in P1. when I write this, I'm really going to think of an alpha that's just in C. And let me assume phi of alpha also is not the point at infinity. Okay. Then I can expand phi as a Taylor series around alpha. Right? So I get phi of alpha plus phi prime of alpha, z minus alpha, plus, and so on. Okay? And we say alpha is a critical point. If the derivative is 0, which will also mean that phi is not 1-to-1 in the little neighborhood of alpha. And I'm going to write it. The image of alpha, phi of alpha here, is called a critical value sometimes. And if you just think of P1 of C as like a Riemann surface, this is just where two of the branches come together for the map. I could if I knew that. Okay. It's auto-focusing, I think, but I have to put it in the right place. Okay, thanks. Good. Oh, yeah, so in this case, I said alpha is not supposed to be infinity, and phi of alpha is not infinity. But if you want to deal with the point at infinity, simply conjugate your map phi by some linear fractional transformation to move those 2 points away from infinity. And it's easy enough to check that well, actually, the value of phi prime may choose, but it's vanishing or not vanishing. It won't change. So this, all right. So now let's look around a periodic point. Okay. So let's suppose alpha is a periodic point for phi, and so that means some iterative alpha is equal to alpha. And if I take the smallest such n is called the minimal period, or the exact period, or there's actually 2 or 3 other words for it. It's not really standard, but it's obviously it's the smallest iterative phi that sends alpha to alpha. Well, that means that phi to the n of alpha will look like alpha plus, I'm just doing a Taylor series expansion, plus some constant phi prime of alpha, z minus alpha, plus z, and so on. But some of those terms might vanish. So let the first non-zero term here be z minus alpha to the e. I'm sorry? Oh, I'm sorry, I was using x here and z there. Yes, I tend to use z when I'm typing things and x when I'm writing them, so we may have to just decide that x and z are the same variable. Okay, so this c is supposed to be non-zero. You choose the first non-zero term. And then this exponent e is the ramification index. No, I'm sorry. I've jumped ahead to do 2 things. All right. Let's just skip this for the moment. I'll go back to that in a second. I actually want to do that for every point, not just for periodic points. But for the minimal, if I take a periodic point and its minimal period is n, okay, then what's called the multiplier of phi at alpha, which I'll denote lambda sub alpha of phi, is just the derivative of the nth iterate of phi at alpha. Okay? And what's the significance of that is that if you take the expansion of phi to the n, I'm going to use these, around alpha, you'll get alpha because phi to the n of alpha is alpha, and then the first term the Taylor series coefficient is this multiplier. I define that to be the derivative of phi to the n, and then you get higher order terms. So what will happen is if you iterate phi to the n and look in the neighborhood of alpha, this multiplier is going to some extent determine what's happening locally around alpha. Okay? All right, so we're going to come back to that in a minute. Now let me go back to what I was starting to do over here, where I didn't need to take the periodic point. Simply if you take any alpha, so this would be any alpha, then the Taylor series expansion looks like phi of alpha plus some constant c minus alpha to the e. Where I take the first non-zero term here, and then this e is the ramification index of phi at alpha. And it's denoted e sub, sometimes e sub phi of alpha, sometimes e sub alpha of phi. I can't remember which one I did. E sub alpha of phi. Okay. So roughly what's happening, I mean, aside from, in the neighborhood of alpha, I mean, obviously you're getting moved from alpha to phi of alpha, but then locally you're kind of twisting around the circle e times. And if you go back and you think about it, what, the map phi is ramified at alpha, so alpha is a critical point if and only if this e is 2 or bigger, because that would mean there's no degree 1 term, so the derivative vanishes. Okay? Because alpha is critical. It's a critical point, or ramification point, if and only if its ramification index is at least 2. And it's easy enough to check that there are only finitely many critical points. And there's a very important relation between the critical points and sort of the overall geometry of the map. Okay? It's called the Riemann-Hurwitz formula. And it says if you add up over all the points the ramification indices, well, this would be a very bad thing to do because the ramification indices are all 1 or bigger, right? So subtract 1 so we don't have an uncountable sum of 1s. So this ends up being a finite sum because almost all the points are not critical points. So the ramification index is 1. And the total sum of these ramification indices like this is twice the degree of the map, minus 2. And there's a similar formula many people have probably seen for any map between 2 Riemann surfaces, where you have a local expression on this side, and on this side you have material that's global. It's the degree of the map and the genus of the two, the genera of the two curves. In this case, our curve is just P1, so the genus is 0, so it ends up being a simple looking formula. Okay. So that was the quick introduction to the geometry bit. I'm going to use. I should mention that Rob Benedetto's talks are going to be similar sort of things to this, except all these C's that we've been using, he's going to replace either with QP or with CP, so it'll be over the p-adics. So you can do this for other fields that have absolute values on them. So you can keep that in mind while we're talking about complex dynamics. Okay. So here's a quick introduction to classical dynamics. And I do mean quick because, right, this is a subject that you can write volumes on. So remember that I defined on that previous slide the multiplier. So what happens is that if you take a periodic point of period n, then locally, phi bn of z looks like alpha plus this multiplier plus higher order terms. And if you start iterating phi to the n, so say phi to the n, which would just be phi to the nm, you see what happens? I mean, alpha just gets mapped to alpha, gets mapped to alpha, so you get left with the alpha here. The linear term, when you substitute it in, you just get lambda alphas multiplying by themselves, plus higher order terms. So if you start close to alpha, and if, for example, this multiplier was less than 1, then the powers get smaller and smaller. You'll stay close to alpha. And in fact, even if the absolute value of the multiplier is equal to 1, you still will basically stay pretty close to alpha. And one can analyze what happens to points near to alpha when you iterate phi. Okay? So the moral there is that if the multiplier is less than 1, or even less than or equal to 1, then locally one can analyze what's happening. Okay? So there are names given to the point depending on what this multiplier is. And we say that alpha is attracting if the multiplier is less than 1. Because what that will mean, if you just stare at this equation a little bit, is that if you start near alpha and iterate phi to the n, the points get sucked into alpha. It's called indifferent if the absolute value is equal to 1. And in that case, if you start near alpha, you will actually stay reasonably, well, sometimes you'll stay near alpha. One can, in fact, analyze reasonably well what's happening. Actually, I'm not sure I really want to stand by that statement. But, okay. And it's repelling if alpha is bigger than 1. And it's sort of a special case if alpha is, well, a periodic point, but also a critical point. So this derivative vanishes. Then it's called super attracting. And that's if the multiplier is 0. So the derivative is 0. And in that case, if you start near alpha, you will really get crunched into alpha very quickly. Although the behavior can be a little more complicated than for sort of the purely attracting case. Okay, so that's just some terminology. So, in the case that you have a dynamical system, maybe you can think of it abstractly, but the set S has a metric on it, so you have a way of measuring the distance between points. What's really interesting is to think about if you start with 2 points that are pretty close to each other, and you apply phi, do they stay close to each other, or do they start to move apart from one another? Okay? And this is really where discrete dynamics, actually dynamics as a whole in some sense, got its start. Because there was certainly a belief at one time that if you took a reasonable sort of map and you took points that started really, really close to each other, then they would stay close to each other pretty much indefinitely. And it turns out that that's not always the case. Sometimes it is and sometimes it isn't. And this lets us break the set S up into two distinct sets. But first we need a way of sort of quantifying what does it mean to stay close to each other or to not stay close to each other. And what one does is goes all the way back to the delta epsilon definition of continuity. So, I mean, a single map is continuous, and this isn't exactly right, but intuitively, a map is continuous if you take points that are close to each other, their images should be close to each other. I know it's not quite right, but that's the intuition. So what we want to do is say that that happens, but it happens uniformly for all the iterates of phi. Okay? So here's the definition. Phi is said to be uniformly continuous at alpha if, I wonder if I can get this right without looking at the notes. So for all epsilon greater than 0, there exists a delta greater than 0, such that for all points that are sufficiently close to alpha, so for all beta, I'll use rho, that metric I talked about at the beginning, but you can use it, if you have any metric space, this can be the metric on your metric space. So for all betas that are sufficiently close to alpha, well, just to get continuity, what we would want is that phi of beta is epsilon close to phi of alpha. And now where does the uniformity come in? Well, I want this to be true for all n. The important thing here, of course, is that the delta that goes with the epsilon doesn't depend on the n. Right? So you can, if you start sufficiently close, all the iterates stay close to one another. And as Rob was telling me, he's going to mention this briefly and then use a different definition of equicontinuity for the p-adics that's more useful in practice. And over the complexes, there are various things which are equivalent to this, depending on sort of what kinds of functions you're using. But this works completely generally for.
Is this equicontinuity or uniform?
Oh, I'm sorry. Sorry. Used the wrong word. Yes, uniform continuity has a definition that everyone knows from their real analysis course, right? That's not this one. Now, this is equicontinuity. And more generally, instead of looking at the set of iterates of a map, it's often convenient to say that a collection of maps, a set of maps is equicontinuous if this is true, where instead of saying phi to the n of beta and phi to the n of alpha, say phi sub n of beta, phi sub n of alpha. Okay. So often it's useful to look at slightly more general sets of maps rather than just a set of iterates. Okay. So, in some sense, the points alpha where phi is equicontinuous are the nice points, right? That's where, if you then understand what phi does with alpha, you understand what phi does with nearby points. So we could can break the complex projective line up into two parts, the nice points and the not nice points, which is not what the points are called. So the Fatu set F of phi is the largest open set such that phi is equicontinuous for all points in this set, okay? You can't, it turns out you can't simply take all the points where phi is equicontinuous because that set might not be open. So if you like, take the set of all equicontinuous points and then take its interior. And then the Julia set, which is where phi behaves badly in some sense, J of phi is simply the complement of the Fatu set. And people say that, well, nice term, that you get chaos on the Julia set. Phi behaves chaotically, meaning no matter how close 2 points start to each other, eventually, if you iterate phi long enough, they move apart from one another. Okay, so that's the intuition of what the Julia set is and what the Fatu set is. And certainly one of the goals of classical dynamics is to describe what these two sets look like. So let me put one example up. You just take phi of z equals z squared. It's actually, so this example you might read exercise. Okay, it's a nice exercise to prove. The Julia set is just a unit circle. It's the set of complex numbers of norm 1. And the Fatu set, well, I don't have to write what it is, it's the complement of that. Okay. So the map sees, well, all right, just think about it for a second. If you're not on the unit circle, the absolute value of z is either less than 1, in which case iterating phi sucks you down to 0, or your absolute value is bigger than 1, in which case iterates of phi suck you out to infinity. However, if you're on the unit circle and not the root of unity, then the iterates of phi actually will be dense on the unit circle, so things will get moved apart. And since the Julia set's closed, you get the whole unit circle. Okay. Here are just a couple of basic facts about Fatu and Julia sets, which I'm certainly not going to have time to prove. One thing that's useful is that the Fatu set of an iterate is the Fatu set of the original map, and the same with Julia sets. So if you're just studying Julia sets and Fatu sets, you can replace a map by one of its iterates. Something that, and this is not hard to prove at all, something that's not at all obvious, at least initially I think, is that the Julia set is never empty. So every rational map, I didn't say this back at the beginning, did I? We're only going to look at, if I don't say otherwise, I'm only looking at maps of degree 2 or bigger, okay? Maps of degree 1 are interesting, but they're easy to analyze. Okay? So there are always points where phi behaves chaotically. On the other hand, it's actually possible, as mentioned, there exists phi whose Fatu set is empty. So there are maps phi, and they're actually not so hard to write down, that behave chaotically everywhere. And this is definitely a theorem over the complex numbers. This last line that I wrote, these two things, if you're over the p-adics, you have to reverse it. Over the p-adics, the Fatu set is always non-empty, and it's very, very often the case the Julia set's empty. That's one difference between complex and p-adic dynamics. Another interesting things with it. J of phi is what's called a perfect set, which means that every point in it is a limit of other points in the set. Or if you like, if you take any one point away from the Julius set and take the closure, you get that point back. Okay? So it has no isolated points. However, it's frequently the case that it's totally disconnected. So it can be a really horrible looking set. Okay, so maybe one more fact about Julius sets, just to indicate the connection between sort of algebraic properties of the map and complex topological properties. Because the definition, for example, of periodic points and pre-periodic points, that's algebraic. You get an equation, you look at its roots. It doesn't have anything about the topology in it. So it turns out that almost all of the periodic points are repelling. Their multipliers are bigger than 1, so if you're near them, you get pushed away. Okay? And there's even a fairly precise estimate. The number of non-repelling periodic points, cycles, thank you, I always do that, is at most twice the degree of phi minus 2, which you might recognize as the number that comes up in the Hurwitz-Genus, in the Riemann-Hurwitz formula, which is not a coincidence. And if you take a repelling periodic point, repelling periodic points are always in the Julius set, because the map is pushing away from them. So close, nearby points always have to get pushed further apart. Okay? So you can look at the repelling periodic points. Look at the set of repelling periodic points. That's contained in the Julius set. That's fairly obvious. What's a very important theorem is that the closure, the topological closure of the repelling periodic points is the Julius set. So the periodic points are actually dense in the Julius set. And once you know this, you can frequently prove properties about the Julius set sort of in a more algebraic way by using properties of periodic points, or it gets used both directions, as you can probably imagine. In the p-adic case, this is not quite known to be true. Could it actually be true? Oh, good. Okay, so Rob's going to talk about this a bit in the p-adic case, so I don't have to do that. Good. But it's a very interesting question in the non-Archimedean setting also. Okay, so the last 10 minutes, I'm going to switch gears entirely and just a little bit of background on some of the number theoretic tools that I'm going to use. And again, if you've seen this, you can tune out. I think probably not everyone has seen all this stuff, so just to get it set. So the first thing I want to talk about are height functions. Okay. So if I take an algebraic number, I'm going to define the height of alpha basically to be the arithmetic complexity. That's the intuition. One way you can think about it, if you're a computer scientist, is if you wanted to specify an algebraic number on a computer, how many bits would you need to store that information? Okay, that's more or less what I'm going to define the height to be, because that's one way of thinking about it. But the actual definition is a bit more arithmetic. What we do is let f sub alpha of x in z of x be the minimal polynomial of alpha. Okay? And then just factor this. Like there's a typo in the notes. That's not good. I forgot to put the. Right. So factor it as x minus alpha 1, x minus alpha 2, x minus alpha sub d, say. In the notes, I could put the leading coefficient in, right? But obviously, there could be a leading coefficient. Oh, yeah. Need to be a little more careful. Minimal polynomial of alpha. Let me assume that the GCD of the coefficients of f sub alpha is 1, okay? So factor out any common factor. Okay. GCD of coefficients equals 1. Then the height of alpha, and this is the capital H height, is, well, basically, you take the leading coefficient A of your polynomial, and then you check to see how big the conjugates of alpha are. So I take the product of the size of the conjugate, but I throw away the ones that have absolute value less than 1. Okay? So that's a nice definition. It turns out for various normalization reasons, it's convenient to actually take the dth root of that. Kind of thing, I'm multiplying d things together, so I take the dth root. Okay? And that's the definition of the height, or the multiplicative height. And for notational reasons, it's often convenient to take the logarithm. The capital H height kind of behaves multiplicatively, the little h height behaves more additively. Okay? And since I'm going to want to talk about the height of points in projective space, sometimes, so we just unilaterally set the height of I wanted it inside. Yeah. Yeah. Because without the dth root, that's the relative height to the field where alpha is sitting, and then I need to take the dth root of the whole thing. Yeah. Okay, so what's the point of these things? Well, they're used for proving finiteness theorems normally. Okay. So we have the following theorem. First, if you look at the points in, say, P1 of K, where K is a number field, whose height is bounded, this is finite. So in order to prove that a set of solutions to some problem is finite, all you need to do is prove that those solutions have bounded height. At least they lie in a number field. Okay. And more generally, if you look at the set of points, algebraic points, whose height is bounded and that are defined over fields of bounded degree, they don't all have to be in the same field. So, for example, you could look at all numbers that are quadratic and have bounded height. This is a finite set. So that's the really important finiteness property of the height. The other property lets us relate geometry to number theory. So if I take a rational function, say of degree d, then the height of the image of a point, phi of alpha, Well, think about what will happen. You'll take alpha and you'll plug it in this function that's raising to d powers. So the capital H height, see, if you raise to d powers, well, it's not quite correct, but more or less, I mean things should get raised to the d power. Okay? And then when I take the logarithm for the little h height, it just becomes multiplied by d. So the height of phi of alpha is quite reasonable. Should look more or less like d times the height of alpha. Okay. Now that's not quite true, but it's true up to a bounded amount, where this depends, the O of 1 depends on phi, on the map phi, but not on alpha. And this relates number theory, because the height is a number theoretic quantity, to the geometry, to what the map phi is doing to the point alpha. And I hope you can kind of see how this will be useful for dynamics, because it's saying that, well, if we iterate phi a bunch of times, we're more or less multiplying the height by d to the n. So the height will be getting bigger, roughly. But there's this O of 1 to worry about. And that'll actually be the topic, one of the topics for talk number 2. But the final thing I'm going to talk about today is Diophantine approximation, which tries to answer the following question. If you take an algebraic number, how closely can you approximate alpha by rational numbers? Okay? So, how close can a rational number p over q be to alpha? Well, that's silly, arbitrarily close, right? The rationals are dense and the reals. Let's assume alpha is a real number. But the question is, how close can you get in terms of how big the numerator and denominator of p over q are? And there's an elementary theorem due to Dirichlet that says you can always get to sort of 1 over q squared close. So if alpha is in q bar but not rational, well, and it's a real, then alpha minus p over q, we can make that less than 1 over q squared for infinitely many rational numbers. Okay? So we can get pretty darn close. Actually, in fact, this is true for, I guess, for any real number that's not rational. Okay? And if you've never seen this before, you might sit down and try to prove it. It's not that hard using a pigeonhole principle argument. It's quite cute. And if you want a nicer challenge, try to prove that this is true. It's actually true with the square root of 5 down here. You can do a little bit better. That's a little harder to prove, but not real hard. Then there's an estimate for what happens if alpha actually is an algebraic number, and this is due to Roth. And this is just a wee bit more complicated. Roth got a Fields medal for it. So what it says is if you take an algebraic number that's not rational, and you pick an epsilon greater than 0, then basically you can't do much better than what Dirichlet's theorem says you can do. There is a constant that depends on alpha and epsilon, positive constant, so that you can't get too close to alpha with a rational number. And the theorem says you can't do better than this constant over q to the 2 plus epsilon. Okay. So Dirichlet says you can get as close as 1 over q squared. Roth says you can't get all the way down to q to the 2 plus epsilon. Okay? And this is quite difficult to prove, in addition to which, it's still the case that this constant c is not effective. If I give you an alpha, and I give you an epsilon, there's no effective algorithm to figure out a value for c of alpha epsilon, which means a lot of theorems in Diophantine equations, which depend on Roth's theorem, and there are a lot of them, are ineffective, and if they prove certain equations have finitely many solutions without actually giving you a way of finding all of the solutions. Okay, so that'll be it for today, and tomorrow we'll start in with heights and dynamics. Thank you.
Any questions?
Yes, the bound in this thing. Yeah, it's relatively easy to give a bound in terms of the coefficients of phi, although it's not so easy to give really accurate bounds, which is sometimes helpful. Yeah. Yeah, well, in the piano case, it's actually not. It's actually quite easy to see where there's an empty Julia set, and it's not so hard to see the Fatu set is not empty. That's the theorem from Rod's thesis. In the complex case, to prove the Julia